Hello and welcome back.
Okay, so this is the topic that we started in the previous class, strain hardening. This is nothing but, deforming the metal at a temperature at which recrystallization and recovery cannot occur, right? And that is why this is also known as cold working. So this is primarily deforming the metal, and it also goes by this name, work hardening. So strain hardening, work hardening, or cold working are all synonymous. So as you do that, you basically increase the dislocation density in the material from a range like this, 10 to the power 4 to 10 to the power 6 per millimeter square to 10 to the power 10 per millimeter square. Okay, so that is the kind of increase in the dislocation density that you can expect when the material is subjected to cold working. Okay, and the strength of the material is related to the dislocation density by this particular equation that you see over here, where rho is the dislocation density. So as you increase the dislocation density, you could see from here that the strength is going to increase. Okay, so that's what we call strain hardening, when the dislocation density is increased due to the deformation which is given to the material. Okay, and that you could see from here also, as you increase the percent cold work or the level of deformation, the hardness and the strength increase. Okay, so today we are going to discuss about the mechanisms as to what exactly happens due to the cold working, which ultimately leads to the increment in the strength. Okay, so it's all about interaction between the dislocations. It is dislocation interactions which lead to the increment in the strength in this particular phenomenon. Okay, so what happens is, when you increase the number of dislocations, when the other dislocations move and encounter these dislocations which are now present in large quantities, the motion of the dislocations over the slip planes will be hampered due to presence of other dislocations in their path. Okay, so that's what I mean by dislocation interactions. Okay, and these interactions can happen in different ways depending on how the dislocations are moving and what kind of dislocations you have, whether you have an edge dislocations coming in the path of another edge dislocation, or you have interactions between edge and screw dislocations, right? So depending on that, you could have different types of interactions which could take place as the dislocations move through the slip planes. Okay, for example, you can have a scenario like this where there are two intersecting slip planes. So let's say we are talking about an FCC crystal, and we know in FCC crystal the slip plane is the 111 planes. So these are two intersecting 111 planes, as you could see from this particular figure over here. And in both of these, dislocations are moving. Okay, so here you have a dislocation on this plane, okay, given by this line over here with a particular Burgers vector, which is given by this, right? And here also you have a similar type of dislocation moving on this particular plane. Okay, and these two planes intersect along this line, which is 0, 1, 1. Okay, or to be more specific, in this particular case it is 0 bar 1, 1. Okay, so now, as you could see from here, as these two dislocations meet on this intersecting line, the new dislocation which is generated due to this particular interaction will lie on the 100 plane, as you could see from here, right?
Now, since 100 planes are not the close packed planes in the FCC lattice, this dislocation will find it difficult to move freely.
Okay, so there is a barrier to the dislocation motion due to such interactions, and this kind of barrier is known as Lomer-Cottrell barrier. Okay, So this is one kind of interaction which could happen between two edge dislocations moving on intersecting slip planes. Okay, but there could be other kinds also, as you could see from the figures over here. For example, you can have two slip planes like this, one over here, right, and another over here. And there are two dislocations moving on each of these slip planes, one with a Burgers vector B1 over here, this line, this dislocation line. And similarly, on this plane also, you have another dislocation with Burgers vector B2 moving, okay? And at some point, these two dislocations will meet each other, and as a result of that, a step will be generated in one of the dislocations, as you could see from the second figure, okay? So as this dislocation xy with the Burger vector B1 goes through the second dislocation with the Burger vector B2, this step is generated over here. This step P prime is generated, okay, on this AD dislocation line, okay. So this kind of step which lies out of the original slip plane is known as a jog. So a jog is a step in the dislocation line out of the original slip plane, as you could see over here, right? So the original slip plane in this case was this particular plane on which it was moving, right? This plane. But it is lying out of that plane. So if you have a step like that which lies out of the slip plane, then it will be known as a jog, right? So the interaction of two edge dislocations in this manner will create a jog, right? Now consider this. Here also we have two edge dislocations, 1 and 2, one with a Burgers vector B1 and 2 with a Burgers vector B2, and these are moving in the opposite directions. So as they meet at a particular point, here you can see in both the dislocations a step is created, right? But in this case, you could see that the step is lying on the original slip plane, okay, for both of the dislocations. So such steps which lie in the original slip plane, which remain in the original slip plane, is known as a kink, okay. So a kink is a step in the dislocation line which remains in the original slip plane, as you could see from this particular figure, okay. So here the step that I am talking about is P prime on dislocation 2 and Q prime on dislocation 1, and both of these are lying on the original slip plane, as you could see from here, okay. So this kind of steps will be known as kinks. Now consider the interaction between a screw and an edge dislocation, okay. So here dislocation 1 is an edge dislocation and dislocation 2 is the right-handed screw dislocation, okay. So when these two dislocations meet each other, one screw and another edge, then you can see what is going to happen to each of these dislocations, okay. So as the dislocation 1 passes by dislocation 2, there is a step generated, as you could see here, right. Similarly, in the screw dislocation also a step is created, okay. So the step which is created on the edge dislocation is of edge orientation, because you could see this is still perpendicular to the Burgers vector, right? So that is why this is of edge orientation, right? On the other hand, the kink which is generated on the screw dislocation is also of edge orientation. Okay, so this is a kink, while the step which is generated on the edge dislocation is a jog, right? Because this is out of the slip plane and this is still lying in the slip plane. Okay, but for both the cases, this is of edge orientation. Now consider the interaction between two screw dislocations, right? Dislocation 1 with Burgers vector B1 and another screw dislocation with Burgers vector B2, right? So as these two meet each other, again you can see steps are generated in both the dislocations, right? So in this case, jogs of edge orientation will be generated on both the screw dislocations, right? So interactions between screw dislocations will lead to generation of jogs of edge orientation. So what is the consequence of these kind of steps which are generated? So that would depend on what is the orientation of the step which is being generated, whether it is edge or screw dislocation on a particular type of dislocation. You have to look at that, the character of the dislocation. For example, the jogs which are produced by two edge dislocations can glide freely because they lie in the slip planes of the original dislocations, right? That is what you could see from the images over here. The jog which is produced, it is still lying in one of the slip planes of the dislocations through which the jog is created, right? And that is why this would still be able to move freely, okay? So the movement of such jogs or such dislocations is not going to be really hampered. But on the other hand, if you look at the screw dislocations, the jogs which are created on the screw dislocations have edge orientation, as I said before. And since an edge dislocation can glide freely only in the plane containing the dislocation line and its Burger vector, the movement of such jogs created on screw dislocations will be restricted, right? So that's what I meant when I said that you need to look at the orientation of the step which is created due to dislocation interactions, right? So in case of screw dislocations, you could see that it is of a different orientation. It is of edge orientation, and therefore the movement of such steps or such jogs which are created on screw dislocations will be restricted, right? So that is how when dislocations interact with other dislocations, their movement is hampered due to creation of jogs and kinks on the dislocation lines. Okay, so this is what we call as dislocation interaction. This goes by other names also. For example, forest dislocation or forest dislocation interaction. This essentially means that the dislocation density is increased due to the cold working which is given to the material, and as a result of that, a lot of dislocations are present in the path of other moving dislocations, right? So this kind of dislocations is also known as forest dislocation. Okay, so there are three ways of looking at it as to how the dislocations would interact with each other. One of them we have already seen through interaction of dislocations which generate sessile locks, or those kind of kinks and jogs on the dislocation lines which cannot move. Okay, so such features on the dislocations generated due to dislocation interactions will be known as sessile locks. Okay, sessile means they cannot move. The opposite of which is glissile, which means a moving entity. Okay, so this we have seen as to how this kind of sessile locks can form when the dislocations interact with each other. Interpenetrating or intersecting slip planes, that also we saw. Dislocations moving on such interpenetrating slip planes will produce sessile dislocations. And then the stress field of the dislocations we can also interact with each other. And that could also lead to impediment to the dislocation motion. Right, we have seen this before. Dislocations have stress field in their core, and therefore, through this stress field also, dislocation can interact with each other through those elastic interactions, kind of mechanisms leading to impediment in their motion. Okay, and all of this would ultimately lead to an increase in the strength as the dislocations find it difficult to move through the lattice. So now, if you look at the cold worked structure, as I said before, it increases the dislocation density. A large number of dislocations is generated due to the cold working which is given to the material, and these dislocations can also take up some kind of configuration, some kind of structure. For example, they can form dislocation cells having walls, having cell walls made of dislocations. So dislocations can tangle like this, and form this kind of cells. And as you increase the level of cold working, these dislocation tangles can take up the form of well-defined cells. Something like this, having distinct boundaries between them. So this can be called as dislocation substructure or cellular substructure. where the cell walls are made of high density dislocation tangles. And the exact nature of this cell structure will depend on the material, the strain rate, and the temperature at which the material is deformed. Okay, so these are the parameters which will affect the nature of this structure which forms after cold working. For example, at low temperature, the cell structure is less pronounced. Development of cell structure is not dominant. And it is also true for low stacking fault energy materials. Because for such materials, cross slip is difficult. And as you know, cross slip is a process which assists movement of dislocations. So for this kind of cells to form, the dislocations have to come and join the cell walls. And therefore, if there is difficulty in cross slip, the development of such cell structure will be difficult because dislocations will find it difficult to move when the stacking fault energy is low, and as a result of that it will be difficult for them to come and join such cell walls, and as a result of that the development of such cell structure will be difficult for materials having low stacking fault energy. And also at a high strain rate, deformation it is not pronounced.
So one of the earliest theories of strain hardening says that the strengthening occurs due to pile up of dislocations on slip planes at barriers. So this pile up causes a back stress which opposes the applied stress, and hence more stress is required for further plastic deformation. Okay, so that is how the hardening occurs according to this theory. Now, the dislocation cutting mechanism of strain hardening that we talked about a while back is different from this theory in the sense that the pileup occurs over long range. While the dislocation cutting mechanism occurs over short range of the order of 5 to 10 interatomic distances. Therefore, this kind of hardening can be removed by thermal fluctuations at finite temperatures. So if the cold work material is heated to some elevated temperature, the effect of cold working or the hardening can be removed or reduced.
Okay, so now if you go back to this alloy tempers with regard to the cold working or strain hardening, you would notice that in some of the cases, after the strain hardening, one more operation of heat treatment is given to the material, right? For example, if you look at this H2 category of the tempers, you would see that it is first strain hardened, and after that some of the strain hardening is removed by partial annealing or by stabilization. Okay, so this is to make sure that some of the properties which might have been lost due to the cold working are to be recovered. Okay, and in order to do that, the level of strain hardening has to be reduced by annealing. Okay, so you can say that strain hardening or cold working and annealing go like hand in gloves. Okay, when one is done, another can automatically come for many purposes, as I said, in order to achieve some of the properties which may be needed in the final component, right? So the other part that we need to discuss now with regard to strain hardening is the annealing. So this is given to restore some of the properties that could have been lost due to the cold working. Some physical or mechanical properties that could have been hampered due to the deformation process. For example, you have already seen that ductility is reduced. So if you want to restore some of the ductility into the material, then it has to be annealed. Similarly, there could be other properties such as the electrical conductivity, which may be also hampered due to the deformation. And if you want to restore some of it, then you need to anneal or heat treat the material after the cold working process, after the strain hardening process. Okay, so this is what we are going to discuss next as to what is annealing and what exactly happens during this process, which leads to restoration of some of the properties.
All right, with that we come to the end of this lecture, but there is more to come on this topic. So I will see you again soon. Thank you.